Fantastic. Love it. All right. All right, y'all, I'm ready when you are. Bring it back in.
Yeah, dude. I didn't forget. I was just gonna wait for you. I'm all over the place.
Chris Cilino is a righteous dude.
Please. All right, I'll go ahead and get started. So I couldn't have asked for a better setup. Alan talked a lot about the theory of how you design packages, et cetera, et cetera. I'm going to talk about once you have a package designed, what do you do with it? How do you build? So, introductions. My name is Chris Cilino. I used to work at National Instruments for about 11 years. Somebody earlier in the evening said the word migration, and that for me is now a cuss word. Oh, timeout.
You're showing the presenter's view. You're sharing the presenter's view with the.
Oh, that's unfortunate.
When you do the share, you can choose to share the other monitor. Sorry.
Put it on join me.
You don't get that? Nope.
There's another button here. This one? Yeah, click the drop down arrow.
And then when
Share screen, and then
just move your mouse there and then click on it. There you go.
all right.
Hey.
Hooray! Ship it.
That's perfect.
Thank you. Right, so I worked at NI for 11 years, and like I said, somebody earlier in the evening used the word migration for some strange reason or another, and that struck a chord with me because I wanted to throw up. I was the guy most directly responsible for the customer's migration experience from the LabVIEW of today to what we talked about at NI Week, this last NI Week, so the LabVIEW tomorrow. Anyways.
Blame Chris.
Maybe. I will be my fault. No, all joking aside, I think that the transition is going to be a good one. It'll take a couple of years, but as a user of LabVIEW, I'm staking my career on it, which is now at Cirrus Logic. How many of you, just out of curiosity, have heard about Cirrus Logic before? Anybody? Just a few of you. All right, so I'm going to, like the first 2 or 3 minutes is me saying, who am I, what do I do, and why am I here? So first off, who is Cirrus Logic? Here's our mission statement. Cirrus Logic provides innovative, high-performance analog digital signal processing products that rock. So we're all about music, sound, audio sort of stuff. As an example of some of the things that we make, we design integrated circuits, so singular packages that fit in other things like headphones for noise cancellation. We not only design the algorithms that do the noise cancellation, we design the hardware that then gets put into larger packages like headphones. We do design some noise recognition or voice recognition integrated circuits as well. So that's who Cirrus Logic is. Single integrated circuits that do audio analysis. Cool. How do we do that? So our process in broad strokes. The reason I'm telling you all this is how I fit into the company. So our process in broad strokes, somebody's going to design these integrated circuits. So you've got some nerds who sit on the 5th floor, and they figure out what should actually be made. Well, before we actually cut silicon, we want to make sure that we designed it right. So we do some emulation inside of FPGAs. We do that to validate to verify the design. Okay, great. So we like the emulation. We ship it out to somebody else. They cut the first versions of silicon, and they give us back the prototypes. And now we start banging on that hardware. That's where my group comes in. We're the validation engineers who get the first, second, and third revisions of the hardware back, and we just start trying to beat the crap out of it. Okay, so that group of engineers, the validation engineers, kind of looks like this. All the folks on the left, they are excellent at doing validation. They know how to do things with hardware that I never even thought possible, which is not saying much because I don't know anything about hardware. But the vast majority of them are, first off, not software developers. And least of all, they know which way is up from LabVIEW. They know what a block diagram is, and that's just about it. Being a little bit facetious. But the reason why I mention that is they actually use my tools, which are written in LabVIEW. They don't know how to edit LabVIEW. So they're like the experts in application who just need tools. All right, so that's the vast majority of people. There in that middle section, a couple of those developers are actually pretty good LabVIEW developers. say 5 or 6 of them. They're kind of in the right at CLD range. One of them is maybe CLA. And then you've got me on the other side of that barrier that has absolutely no idea what validation even means. But I can program the hell out of LabVIEW, right? So they hired me to work with these folks who have great application knowledge, some LabVIEW knowledge. They put me in the middle of them and contractors. Those are the guys on the right who also don't have any validation knowledge. But again, they know how to, there's a bunch of them know how to write LabVIEW code. So I'm the guy that takes application requirements, I design APIs, and then I work with these other developers to actually do stuff. So this is my group's charter. The whole entire reason for our existence. We're a group of mixed signal audio engineers whose purpose is to maintain the high quality of Cirrus Logic products and reduce the cost and execution time of validation. That's what it all boils down to. By designing and maintaining software infrastructure that will scale with the growth of Cirrus Logic. Now this starts to smack of s'mores. We're talking about maintaining software infrastructure. We're talking about scalability. Smells like packages. Right? Okay. How do we do that? So we're going to zoom in on that middle section. Over there on the left, those are the engineers who've got a lot of validation knowledge, some LabVIEW knowledge. And they're the ones, like I said, who come up with these application requirements, API designs, reusable customizations and extensions to IDEs and even bug fixes. They'll actually even edit some of our source code. They work with me and the engineers over with our contractor, and the result of that is we spit out frameworks, utilities, tools, architectures, executables, you name it. How do we do that? It's this little thing called continuous integration, AKA a build process. There needs to be a way of taking the source that everybody, well, I shouldn't say everybody, that a handful of folks can edit and then turn it into something that everybody can use through VI packages, executables, and installers. So we get requirements in and we push distributions out. Distributions are VI packages, executables, installers, et cetera, et cetera. All right, so continuous integration is the key. That's this build process that turns source into distributions. Step 1 in making that happen, engineer your software. You design your packages. Now, practically, what does that look like? This is an example of our directory structure inside of Perforce. Yes, we use source code control. So really, step 1 is use source code control. Step 2 is you organize your packages, the source of your packages. I'm calling them components. It's just a different word to mean the same thing. According to that directory structure, every component has a name. Every component has a version inside of Perforce. So there's the 1.8 version of my library. When it goes final and I call it stable, I branch the trunk, and now the 1.9 version is built. We can always get back to the 1.8 version. It's fantastic. So that's that second layer, the component version number. Underneath that, the build directory, that's everything that you need in order to turn that component into an export, an executable, a VI package, a DLL, whatever. That consists of typically a build specification. In LabVIEW, that build specification is the LabVIEW project and the build specifications in the LabVIEW project. If you're making VI packages, that's the VI package build spec or VIPB. So that information, those build recipes live inside the build spec folder, and then there are custom build steps that get executed at time of build. That's what that second directory is there for. Skip the export directory. We've got source. That's all the stuff that's going to get turned into your distribution, your export. And there is a source directory, but I've got other directories that expose that source. So I might have my source that gets installed to LabVIEW, but there might be a test stand flavor of it. So it's the custom step. It's the modules that you call from within inside a test stand that are actually built on the source, which is in LabVIEW or whatever other language. Or maybe there's a vendor API, like I'm wrapping, I don't know, an Agilent API because I didn't actually like what they did. I want to make my own custom version of the API, so I wrap it as part of the source, and then I make an API. That's great. This is an organization that's worked very well for me. If you guys are wondering, how do I actually organize my reusable libraries or my packages on disk, this has worked very, very well. Now, take a step back. I keep on using these goofy words, component. Question.
Do they have each component its own repository and for control, or are they all in the same repository?
So the concept of a repository in Perforce, I don't know that actually makes sense.
Yeah, so you have just a...
We have one gigantic...
so that's how centralized works, and you just check out what you're working with.
That's correct. We don't have a local repository on the machine. We have the server that houses all of this stuff.
So the only thing is, if it was decentralized, I would suggest each component has its own repository.
Oh, sure. That makes sense. Okay, so now some definitions. If you talk to me for more than 5 minutes, you'll figure out that I like defining words. So I keep on using the word component and export. Here are the formal definitions that I have actually codified, and I'm teaching Cirrus Logic to use. I'm saying an export or a component is an ordered collection of software that's designed to accomplish a specific task. It's designed to be reused by other components by exposing a public API, and it's designed to be built into versioned exports for other components to use. A lot of this mirrors what Alan was just talking about, except for point 2. I had never considered the client owning the API. I'm going to have to scratch my head on that one. But up to this point, I've said that a component is responsible for exposing its function through a contract. That is the API. If you break the contract, that's where you get homicidal people coming after you. So be it.
I'll submit there is a bit of a delta between the components if you find it in a package, because your components are still functional definition of
That's fair.
pieces of software,
Yep.
as opposed to pieces of stuff that changes together. The difference between your perspective as the developer and the perspective of the end user, and that is an end user facing perspective, which is okay.
That's fair. That's fair. Okay, last thing, an export. It's a versioned atomic package, non-divisible, created by processing some portion of the component source through an automated build process. So, yeah, components, from components spawn export or exports. An example is you might produce an executable, but you also need to produce an installer that installs that executable. You might need to make a DLL, and then the API that exposes that DLL inside of LabVIEW. So you need to make an API and the DLL itself. Both of those are exports of the same source. So you can have N exports for a singular component. Okay. I jumped ahead of myself and explained this when I shouldn't have. All right.
So these things, these build exports, are this ordered alphabetically? Not like a reason
No.
you have exports? Okay. I guess that's what threw me off. Like the source to me is the most important part of the component.
Oh.
And the export's like at the end. But
The reason why I have export here is export never makes it into source code control in Cirrus Logic until an export has gone final. So I might make build 137. I don't care about that. When I make the F0, which is the first build of the final, then it gets checked in. That's almost a signal to everybody else, this component is final. Don't touch. All right. And we got lots of other rules around that. One of the cool things about my job at Cirrus Logic, like I said, these guys are not software developers. Well, while I was at NI, I spent 7.5 years in R&D, and so I learned a lot of these practices, and now I'm getting to convey that knowledge to them. That's an incredible amount of fun. I really am enjoying that a lot. All right. I already walked through this. Okay, so the first step in doing continuous integration is organization. So I organize every component has this structure, which means an automated process can look inside of one of these things and know what to expect. It knows that there's a directory called build specs. That's probably where your build specs are located. Good call. Yeah, I know, right? Well, the other way that, beyond just this directory structuring that defines a component, I also have a text file that defines what the component is. It says stuff like, what is your unique name in the world of all of our components? And that unique name might look like crap, CL_G3 digital interface. That's not very user-friendly. So I came up with a product name as well. Sidebar, I stole that from VI Package Manager. They also have the concept of a universal name and a product-facing name. So my hat's off to them. The next section is, what can you export? So yes, you're a component. Great. What are you gonna make? So I say there's an export definition name. It's called digital interface.vipb. That points to my build specification, which is a VI package build spec. Now, I don't want to tie any sort of meaning into a file extension. So what I did is I said for each one of my exports, which is a comma delimited list, there's only one export here, tell me about yourself. So the digital interface is defined here. I say you are of type VIP. It could be of type DLL or of type executable or whatever. And then we're going to go over commit behavior. Like each export can say, once I'm made, where do I live? Where do you deposit me? On the network? Do you email me to somebody? Do you text somebody that I'm done? What's the commit behavior? All right. So the fundamentals of my build process is ordered and organized source and this file. With those two things combined, I'm going to show you now my application, I hope. Let's see if this works. All right. Fingers crossed. Okay. This is like the pre-beta of the version 1 of the application that I'm actually planning on releasing. I actually have the next version, which I'll show you later on. But the very first thing that I'm going to do, this is coming over the internet right now, right? Yeah, okay. The very first thing that I'm going to, well, start the program. That's great.
Hit the run arrow.
Yeah, I know, right? Like I said, it's the pre of the beta of the version 1. What this program does is, first off, scours my hard drive and says, where are all of those text files that define components? I'm going to go snag all of those. And then, based on what's inside of those text files and some other information that I'll walk you guys through in a little bit, I'm going to build the hierarchy of your components, because packages depend on packages. So if we're going to build these things, you've got to build them in the right order. So you've got to find out who depends on who. All right. Oh, man, this is going to be rough. So I populate a ring control. Here are all the packages that I found. And I say, tell me about Clive. Is that Clive? I can't read it. Up one. That's Clive. And he says, all right, so here's some information about Clive. This is the package path, the product name, all the sort of stuff. And then here is everybody that I depend on. And here is everybody that depends on me. So this is both a downward-facing and upward-facing view. If I expand any one of these guys, I see the same information. So here's everybody that he depends on, and everybody that depends on him. Okay, so this is kind of cool. Now that's for a singular package, but that doesn't tell me any sort of a build order. So I'm going to come over here and build, say I want to build Clive, and I say analyze. Here's the build order. You start with Clive and then build everybody who's on top of him. Or I can change the mode to build dependencies, analyze, and that builds everybody who's underneath me in the right order. Okay, so this application, the whole entire basis behind it is you give me a singular component, and if there's a change to that component, that could trigger changes to everybody who depends on me. What's that build order? Or, given that component, who all do I need to rebuild that's underneath me? You can get either one. The last thing is, let's say I don't just want to build Clive, I want to build a couple of things. So I call analyze, and it's going to take these three components and determine the build order of all of those different packages. So that's both looking down for dependencies and looking up for what I call bubble up. Questions so far?
Have you had to deal with the situation with circular dependencies?
Do not detect circular dependencies.
Which is instantly...
Oh yeah, the lock program. Yeah.
So you do detect circular defense.
There's a symptom. Ideally, if you have flashing red, don't do that. But yeah, that's one of the things that I have to put in place. So this, this build system, one of the things that Alan mentioned up front was the cost associated with doing package development. You have to do documentation. You have to announce when your packages are done. This has nothing to do with writing code. One of the things that I'm breaking Cirrus Logic into is infrastructure is important. It is costly, but in the long run, it's going to pay off big time. This is infrastructure. This is not making us any money at all. Not directly. In the long term, it will. And
Chris, do you guys have build servers where you host all these things? Just say now build all of them.
Wouldn't that be nice? We'll get there. We'll get there. So you're looking at the guy who knows what continuous integration is at Cirrus Logic, which is really a lot of fun. It gives me a lot of autonomy. It gives me a very long rope to hang myself. That's the downside to it. But it's really a lot of fun. I get to take a lot of the really good lessons I learned here at National Instruments and then customize a solution for Cirrus Logic. And in the meanwhile, hopefully make something that I can distribute to everybody. So that's where I'm going with this. Because wouldn't it be nice if you followed these rules, you got all of this incredible behavior? We haven't even gotten to the cool stuff yet. All right, so that is a small sample of my application. I can analyze dependencies and spit out a build order. Now, I'm not telling you what you can do with that build order yet. I just told you what the right build order is. We'll get there. All right. That's never going to work. Oh, my. All right, so how did I put that application together? It's composed basically of 5 classes. The first one is the build analyzer, and you saw pretty much what the build analyzer can do. Analyzes a component hierarchy and determines build order. That's great. Second class is component, and this one's really kind of lightweight. All it really does is parses that file that I told you about and then brings exports into existence. Exports abstract the engine that turns the source into an export. What's an engine? VI package manager, LabVIEW, C compilers. It's not limited to any IDE. It's an abstraction behind the build engine. So long as you give me source and a recipe, we're good to go. All right. Once you've made the thing, the export, the executable, the DLL, what do you want me to do with it? That's what commit is. And one of the last things is I decided to keep build, component, export, and commit completely agnostic of source code control because different source code control providers have different models of execution. Perforce has the idea of checkout and commit, whereas SVN doesn't, and it's just backwards to me. So you guys can take care of whatever you want to do your source code control. All right, so we're going to dive into the Build Analyzer API. You're looking at it. If you give me an array of component definition files, then I'm going to build a tree under the hood. And then if you tell me which exports you'd like to build, how you'd like to analyze them, I'll spit out ordered exports. That is the API. This third VI, it's just it's UI candy. It's if you want to know information about a particular export, I'll display it to a tree on your UI. And that's actually what was. Let's see if this is going to work. How do you get up? That is this. That one singular VI was responsible for populating this tree. Okay? The last part of the API is... Oh, don't worry about it. Actually, we're going to get to what's under the hood here shortly. And the last thing is you got to clean up after yourself. Then I give you a couple of properties. We're going to talk about what a working set is here shortly. But the portion of the component definition.txt file that I actually use is what is your unique name and what is your product name. All right, so now we start getting into the real nitty-gritty. Okay, great. How did I do this?
Yeah, there you go.
Who's heard of my LabVIEW containers? Okay, we got a couple of hands that are going to go up. I could spend 2 hours talking about LabVIEW containers, and yeah, I know, right? It's something that I put together. Think of it as a two-way linked list inside of LabVIEW, or another way to think about it is a tree inside of LabVIEW. The summary is the LabVIEW container allows you to store named data of any data type in hierarchical relationships. Two-way link between parents and children. A child can only have one parent. A parent can have n children. This looks a lot like the way that we define components or packages. Kind of useful. So that's the reason why I modeled it. I used the LabVIEW container to construct this hierarchy. All right, now we're going to talk about algorithms. How did I actually do this? I start off with what I call a working set. A, B, C, D, and E, those bubbles, all represent containers. They came into existence based on that text file. And then each one of those containers had a way, which I'll show you guys in a little bit, of telling me who do I depend on? What are the names of the other elements inside the working set? All of the other libraries that I'm aware of. What are the other names that I depend on? Well, I depend on B and E. Those are just the names. Those aren't the actual containers. Okay? So step one, I'm going to create another set. I'm going to call it a dependency tree. It's going to be empty up front. And then I'm going to copy A. A still has what it depends on, B and E, right? Step two, go find B and E, copy them, and add them to A. Okay, so it's starting to look like a tree. Now, trees lend themselves very nicely to recursion, so I do. Recurse down B and E now. Go find D and C. Copy them. Okay, you'll notice I put a ... for C because it goes on and on and on. So I've got this A container just hanging out. The last thing I'm going to do is add it to the dependency tree. So now, if you tell me to start with A, I have all of A's dependencies as a tree. And B knows what he depends on, D knows what he depends on, and D knows that B is his parent, et cetera, et cetera. Do that for all elements in the raw working set. Questions? I'm going to actually show you the code that does this shortly. Yes?
Could this somewhat be related to like graph theory with like relationships between nodes and?
Because that sounds really smart and sophisticated, I'm going to say yes. I don't know. I brute force this. I'm sure that there's more efficient ways of doing this with graph theory.
Yeah, for sure.
Now, this is for the dependencies down. I'll just show you the other. There's another way of doing not a dependency tree, but a dependent tree. So who all depends on me versus who do I depend on? It's the same kind of game that I play. All right, so now we're going to actually look at the VI that does this, if I remember where it is in my source. What do you think about that? Oh, sweet. Stop. All right. Pay no attention to this man behind the curtain. Right. So I want this guy. All right. This is the dude that starts off this whole entire business. For me, one of my conventions is that VIs that have a red border are recursive. Okay? So, how do we start this whole entire business off? The first thing is I create that dependency tree. That was that blue line. There's nothing inside of it. It's empty. Then I have my working set, and I get all of its children. That was A, B, C, D, E, whatever. And I start processing those in this for loop. So for every element inside of the raw working set, do this. Well, I need to get its unique name. I copy it, and then I recurse. This is what the recursive algorithm looks like. I wonder if I can do this. This could be kind of cool. Right. Okay, I just copied it, Now I need to go back into the working set, get its children, and then I copy them and add the, and in effect, this VI is stuffing B and A. And then I recurse, because now it's time for me to process B's children. One of the reasons why containers are somewhat difficult to use is because all of those lines have the same color, and it's difficult to keep track of which one am I operating in. That's why I went through that little exercise up front with actually showing you what's going on with these bubbles. It's kind of hard to follow. But the cool thing about containers is this is just one of the many applications of containers. I'm very passionate about this. In case you missed it, if you want to download the containers, you can at this bit.ly. bit.ly/LV_container. It's pretty powerful. It's a VM package, and it's good stuff. Check it out. Any questions? Okay. How am I doing? Have I lost anybody? Is anybody ready to go to sleep yet? All right. Right. So I've got all of these different. I've got A, B, C, D along this line. How do I actually turn that into a build order? Okay. So we actually start processing starting at A, and I take a look. I build an array that has A's export inside of it. Now, A only has one export. That's why there's only one element in his array. And then I recurse. I make more arrays. Export array for B. Export array that contains E. And I recurse again. Export array D, export array C. Now I go back up the tree, and I concatenate these arrays. Right? Okay. Now something interesting is going to happen. Is BD going to go first, or EC going to go first? And they all get munged together with A. I'll spare you. It's a trick question. It doesn't matter. Because it turns out they don't depend on each other. BD doesn't depend on EC. So they can get built either way. Make sense? Now, I always start with the most leaf node and then work my way up. So C was the thing that had no dependencies. He's kind of flying out there in the middle of nowhere. So I'm going to just build him first and then work my way up the tree. All right. One of the things I showed you in the application is, what if I don't just want to build A? I want to build A and J and H and whatever else you want. Well, I played the same. Let's imagine that we had a J export array, and he depends on E, K, C, D, and H. Great. I'm totally making all this stuff up now. If you fall asleep, I won't be offended. All right. What I do is I find the earliest instance of J's first element, E, inside of A, and then I replace. But there's a problem. Now I have duplicates. Oh, damn. So the game that I play, I start at the end, and I say, oh, there's a C, there's an H, there's a D. I already have a C. Kill that C off. So the oldest one always wins. The result is that. That is now your build order. And boop, out come these exports. They're objects. And they're ordered according to that array. Questions? All right. I don't want to look at code. Do I? Yeah, okay, I'll take a look at code. Right. I'm going to clean up after myself. Hold on. Okay. I wrote this presentation yesterday, so it's still a little bit bumpy. I'm not going to look at code. What I am going to show you is what you can do with an export. I have this ordered set of exports. I've written an abstraction layer. We'll call it a BAL, build abstraction layer. I just coined that. That's mine. You guys get it. All right. So these are all the different things that an export can do. I'll spare you all the details. It does have constructors and parallel destructor. I should have called it deconstructor. There's a way for discovering what an export's dependencies are. Then, once you have an export, you're probably going to want to build it. And that's what actually invokes the engine. I'll show you guys the code shortly. You're probably going to want to submit it once you have it built. But you might not. You might want to revert it. You might want to preview what's going to happen if it actually gets submitted. So I got a lot of this from my days here at NI and the different functions that you can perform. You'll notice there's nothing specific to LabVIEW inside of here other than they are VIs. But this could go for any language. This could go for any build engine. That's the way I designed it. And what I've first abstracted away is VI Package Manager, because the vast majority of our code at Cirrus Logic is delivered to the masses through VI Package Manager. So that's the very first engine that I abstracted. So we're going to take a look under the hood for what does it mean for a thing to broadcast what its dependencies are. If I give you a component, how does it tell me what it depends on? Let's take a look at that. Pardon me. So this guy takes an export in. Oh, that's not what I wanted. We're probably going to need the actual implementation. Yeah. For a VI package, the way that you get its dependencies is by looking at the VI package build spec. Now, this is going to be different depending on the engine. VI package build specs are just XML files. So I'm using LabVIEW to parse this XML file, and I ask for the section called Additional External Dependencies. You get the array of nodes, and no, I really don't understand what this stuff means, but insert reasons here. That's going to give me the node's value, which is the unique name of the export. Ooh, unique name. We saw that before. That's what appeared inside of that text file, and I created a container with that unique name. That's how I link all these things together. Okay? Now, the way that you go about getting dependencies is going to vary. Like LabVIEW doesn't have any way for broadcasting its dependencies. So to steal from Alan, initially I asked him, hey, you had this reusable package that you broke out of your executable. Was that package part of the same project? And the answer was yes. So that makes it easy to say that project depends on that package because it's a part of the same project. What if you had a project whose only purpose was maintain reusable code to be used by other projects? How do you go about linking all of that stuff together? Kind of rough. You could develop your own text file system. Sure, you can do whatever you want. This is how you do it for VI packages. You can develop any other system that you want. That's the reason why I made it overwritable. Questions? Next, I wanted to show you what building actually does. This is where the really boring stuff is. You would think this is where it's so exciting, but it's so terrible. I need to refactor. Oh, God, I did it again. Yeah, it was easy. All right.
You just run a few wires.
That's right.
LabVIEW.
Dude, VI Package Manager, or VI Package Builder is awesome. So I'm not proud of this code. We'll just say that. This needs to be refactored into a very nice state machine because it's anything but right now. The short of it is...
Give me your CLA, sir.
Yeah.
Oh, I think I'm going to do right.
Oh, nice. The short of it is I take all of the source and I add it to a dummy project. Then I tell LabVIEW, take that dummy project and save it to a temporary directory. Is that Jim?
Yeah.
What do you say?
VIPM loves YouTube.
Oh. Right, so I take all the source, add it into a project, I save it, and then I tell LabVIEW, save it to a different location. The reason that I do that is all of my source lives in So, number one, VIPM can't build source that lives inside of user lib for good reasons, but I needed it to. So what I do is I copy all of those VIs outside of userlib, but that breaks all of the relative links between them. Even though the relative paths stay the same, the trick about userlib is they're not relative paths. They're absolute paths. So you might have userlib \a.vi that relies or calls userlib \bvi. They're in the same directory, right? If you copy them lock, stock, and barrel to a different location on disk, they won't be able to find each other, which is incredibly irritating. The way that you should be scratching your head. If Stephen stuck around, I actually had an hour-long conversation with Stephen on how I want LabVIEW to maintain relative paths to VIs that have userlib in their paths, because they don't. So he's the one who gave me this trick. Add everything into a project, save that project somewhere else. Now LabVIEW mystically, magically, linker magic, fairy dust here, maintains all of the relative paths and updates everything. So that's what I'm doing. So now I have my source in a temporary location, and I invoke VI Package Manager from there. That took me 3 weeks to figure out. Not fun. So that's all this is doing. It's copying stuff around. Whoa. Hopefully this works. All right. So copying stuff around. Look, there's where I save a project. That's exciting. Here is where I upgrade a package's dependencies. Let's say that B depends on C. I could have started with A and B. So that A depends on B. We start building from the bottom up. So I'm going to build B first. And it just got revved from version 1 to version 2. Now I build A. I need to update A to refer to version 2, not version 1. The way that you do that in VI Package Manager is by changing the VIPB, the build spec itself. So that's what, So he's suggesting that I use the VIPC. Right? Anyway, this is how you upgrade package dependencies for a VI package. Please. More XML stuff. Really cool things. You all are amazed. Yes, the problem is, so Jim is saying that the VIPC stores all of the VIPBs together. The problem is I don't necessarily build all of the same software at the same time. So I'd have lots of different VIPCs out there. So Jim, yes, I am experimenting with some stuff. I'll probably be calling you later.
That was precious.
Yeah.
What will you be calling you later?
Best friend. All right, so we got, what was it? Oh, how a package returns to me its dependencies. Depends on the build engine. Like I said, we look at the XML file for a VI package build spec. Show you how you build. Oh, the one magic thing I actually didn't show you. This is where, Jim, you owe me money. So this is Jim's API for VI Package Manager. This is what will actually... Watch this. Okay, so this is where you actually programmatically invoke VI Package Manager by passing it a build specification. And inside the build specification, the path is there to your source. So the VI Package build spec gets turned into a VI package, and everything is grand. And VI Package, that API costs about $750. So that's per license. He's actually not going to say anything. Oh, there it is.
He just didn't say which mail of which one.
That's right. What I was actually going to say is it cost like $2,000, and then I was going to tell him to split the difference with me. Anyway. Yeah, so you do need a license to VI Package Manager to automate VI Package Manager. This is one of the things in the API. In case you're curious, add-ons, there it is. You can do lots of stuff with automating VI Package Manager. Like you can install VI packages. You can do stuff with adding VI packages to the local library. It's a pretty powerful API.
So to be clear, the stuff you're editing here in the XML for the package build is not stuff that's in the API for VI Package Manager.
There is some. Now, which begs the question, why didn't I choose to go through the API to do it? Jim, guard your ears, because the API can be slow sometimes. one, and two, on numerous occasions when I've invoked the API, VI Package Manager will hang. And I'll have to shut it down and restart it. So I'm actually going to be wrapping this function in a sub-VI. It spawns a separate process, and if that separate process becomes unresponsive, I'll kill it and restart VI Package Manager. Not there yet, but that's the reason why I try and invoke the API as little as possible because, yeah, see, I've had to do that too.
Yeah, no. It's interesting because that's XML stuff. If there's not an API for it,
No,
that makes sense.
there is. I'm just trying to minimize the amount of times I have to go to VI Package Manager.
Right.
So, nonetheless, this wouldn't be possible without Jim's work. So, my hat's off to Jim. If you guys are considering it for your company, I endorse it. I recommend it. And I'll give you my mailing address for a check later. All right, so that was how I get a package's dependencies, how I invoke the build engine. Both of those are, of course, overwritable. It depends on your environment that you're actually using to do the build. And the last thing is, you got to commit the thing. Like, you built the export, you got a VI package. What are you going to do with it? All right, so an export has a commit object inside of it. I forget what this technique is called. I think it's decoration, where you can have, as a part of a class's private data, another class that's overwritable. So it's almost like you're giving it behavior. My export has the behavior of commit, and that is overwritable itself. Strategy pattern? Okay. I forgot that. Great. So here is the submit override. The specific submit got created earlier on by the export via factory pattern. Right. So remember when I told you inside that what was it? Component dependency.txt file that there was an export behavior and it was a string. That string was actually the name of a class on disk. And so I find that class on disk, bring that class into memory, pass it down the line, pass it right here, and now this will dynamic dispatch to that particular behavior. In our case, I have G3 VI package behavior. G3 is the name of my group. This is a VI package. There might be other groups in Cirrus Logic who want to do their own flavor of commit. Maybe they have their own server somewhere. I don't know. Don't care. Yet. I'm sure that I will shortly. What we do in G3, we have a server called Samba. So once the export is created, I copy it up to the server, and now it's broadcast out for the world to use. That's what commit looks like for me. It could vary depending on your component. Maybe it's an executable that has no commit behavior. Maybe, I don't know. You could dream. You could do all kinds of stuff. All right, so those, I think, are the most interesting overrides. And now I will show you the more developed version of my build system. This is a little bit more mature. I haven't released this yet internally. So I start up, and first off, this is telling me what's going on at all points in time. All right, this is the same behavior, but as soon as I select an element, you'll notice that on the right, it tells me what the build order is. And as I add more things to it, that list gets longer, and maybe stuff gets reordered. So that's kind of cool. And I can change this to build dependencies or build only the selected ones. Now, let's see. I'm going to do this. Wait for it. Yeah. Okay, reusables is one of our very most base unstable packages or unstable packages. Lots of people depend on him.
Unstable.
One of the most stable ones that we have. Right. So you'll notice that the order in which I specified things over here does not equal the order over here, because I don't want the person who's specifying what they're going to build to have to know what the right order to build is. So I'm going to figure all that out for you. Make sense? Okay. You hit next, and that kicks off the build. This is clearly simulated. All right, great. So as you... Oh, no. I only put a half-second delay in there. I could have done a whole lot more. Actually, we have 54 components. It takes me an hour and a half to build our entire stack, which is not bad because it took me an hour and 30 minutes to build the DAC assistant.
So if it wasn't simulated, we'd be building it on your machine.
We'll get there.
Okay.
Yes, it would be building it on my machine today. All right. And then you can commit or you can go back. You delete the exports and then, hey, what do you want to build? So that's great. So that is going to be this version. This is like version 2 of 10 that I had envisioned. Because I don't want to use a UI to do this. Whoops. Apparently I didn't comment out enough code. Abort! Oh, God. And pay no attention to that man behind the window. Product placement. Here we go. All right. Great. So this is
time they've gotten product.
He owes me a lot of money. Right. I don't want a UI to do this. I want to kick off a process that runs at midnight every night and analyzes all of my components, figures out which one needs to build, and just goes does it. We're not there yet. Like I said, you're looking at the sole guy at Cirrus Logic who knows what continuous integration or build process is. So I'm having to grow all of this stuff from scratch, and I have to do it in the right order. What I mean is I have to show value at every stage of my development. My managers, I need to be propping them up and saying, now I can do with this. You just gave me 2 months, now I can do with this. Which means I can't build the final thing. It'll take me a year. So I have to build it in the right order. This is the next stage. All right. So if that's the next stage, let's see if I set myself up for success. Oh, I kind of did. The application that you just saw invokes those 5 classes in a 4 parallel looping queued state machine architecture. Oh, Jim Kring has left. Son of a... Oh, there you go. Jim, I thought I lost you. All right, so the top loop handles UI events. You guys are used to seeing this. The middle loop is the application model. Just because a user presses a button doesn't only necessarily queue up one action. It might queue up 5 different actions, like gray out a button on the UI and kick off the engine. So that's the model. It's given an input, what are all of the different actors that I need to talk to? This middle loop is kind of like the traffic cop. Okay? Then we have the UI manager. This is the one who's responsible for updating control values or displaying messages to the user or graying out buttons, which is all mind-numbing stuff. And then you have the build engine. So what does it actually look like? This I'm a little bit more proud of. Not much, but a little bit more. Right, so event handler, traffic cop. You guys will recognize this API. I stole this lock, stock, and barrel from the sample projects that NI ships. Then you have your UI message handler. This is where you do stuff like enabling or disabling buttons and nonsense. And then, look, here's my build process right there. Actually, this is where I would invoke the export function, but I didn't want to do that now. And I could get a raise right now. See, 300. Look at that. I just improved efficiency. Yes. All right. Right. So that's just the general architecture, and that's okay. I mean, like I said, it's going to work. I'm nowhere close to satisfied. What I want, multiple build engines coordinated through a singular master. I want to be able to spin up N of those builders that process N of those exports in the right order and make them all simultaneously when possible. I want those engines to communicate with each other through TCP/IP because I eventually want those engines to live in separate virtual machines and eventually separate machines that have N virtual machines on them. So I want a build farm. Now, like I said, it takes an hour and a half to build my entire stack right now. That doesn't justify this. But the time will come that it does. So this is me architecting ahead a little bit. Right now I have those 4 looping structures. I need a way of bringing in engines into existence dynamically. Smells like Actor Framework. Smells like DQ. I know. Smells like the Delacorte Q message handler. And right now I've pit these 2 up against each other. They don't even know it. I'm trying to figure out which one is the best fit. Whoa, did you see her? Fight! I know. It got cold in
It
here.
was number 57.
All right, so the last thing is, I want to integrate this with Jenkins, because I was talking with Alan later last week. Jenkins apparently, I don't know how, but has the ability to pull a source code control provider and ask, do you have code inside of you that's changed? Which is one of the core things that I need. I don't know how to do that, don't know how to package it into my stuff. I'm going to be investigating that. Or I could steal Alan's system. Alan's going to give me his system. Actually, he's already published it online. In case you guys haven't seen it, I should have put a slide in here. It's called the Continuous Integration Project.
Continuous integration project.
Right.
Our install process really kind of sucks the rest of this straw. But it works pretty well. I like it.
So what Alan has done, he wrote his build abstraction layer over LabVIEW. I've written my build abstraction layer over VI Package Manager. Sounds like the two of us should meet and combine our work together, because then we'll have two abstractions. One of the requests that I have for Alan's work is that it manage dependencies. Right now, they don't have the concept of a build order. You specify statically what the build order is, and you're off to the races. I think.
Yeah.
Sure. So that's one of the reasons why I want to publish online, and I intend to, in short order, my build analyzer, so that everybody can have it, including these guys.
Probably a way we could put all of those parts. Jenkins programmatically fire off and
Love it. Love it. That's the reason why I wrote those 5 classes the way that I did. They have singular responsibility. We can take them lock, stock, and barrel, or whatever we want to do. So Alan talked about how you design packages, what the borders and boundaries are, when you know you got a good package or a bad package. Once you've designed all your packages, how do you actually make exports? And that is all I have to say about that. Any questions? If not, I'll cut you loose.
one more short
Yeah.
thing we're
All
going
right,
to do.
so 5 minutes.
So, thank you, Alan and Fabiola, for allowing me to speak. I've had a last quarter we had a presentation that the presenter joked he's been backlogged for 3 quarters. I have a presentation that's been backlogged for 3 years now. Initially, when I suggested it, I was told that, oh, you just presented last quarter. We want to wait a little while before you're given a chance to present again. We don't want the same people presenting over and over and over again. And a couple of times, it's because we haven't been tracking it through the forums. It's, oops, forgot about it. Can you remind me next time? And so it has been 3 years, and so the presentation's about FPGAs. I did an FPGA-based project. It was my first and got in over my head in some ways, and there are certain pieces that I had to just sort of skip, at least on the FPGA side, where I just did not have the knowledge at the time, and one of those was implementing some code that works great in regular LabVIEW, but had to deal with dynamic array sizes, which you can't have in FPGA, as well as a number of functions that just really don't exist in the FPGA fabric, but do exist in regular LabVIEW. And so the project ended, I survived it, and over the time since, I went back and said, okay, I couldn't get this code written at the time, I had deadlines to meet, can I get it working now? And the answer is yes. I have since been able to go back and implement code that deals with dynamically variable array sizes. They do have to be bounded, but I have example code that I was able to write code in the FPGA that could work on 1 element one time, 5 elements the next time, 10 elements the time after that, and also look at how can I take that code, which may have taken a larger portion of my FPGA fabric and expand it out not from one channel to handling 10, 20, and even 64 channels simultaneously, because it was a time-weighted data averaging mechanism. And how do you turn that into something that, oh, it takes 10% of your FPGA for one channel, how do you get 64 of those in? We don't have 6400% utilization available on our FPGA fabric, especially because the project was working with one of the smallest FPGA slices there was. So the presentation itself, because I did do this more as an academic exercise rather than the code's never been used anywhere because the project was long gone, I put easily a man-week's worth of effort into going back and trying different ways and how do I create this code that is so easy in LabVIEW, yet so difficult in LabVIEW FPGA. And so I think people here in this room who are not conversant with FPGA would learn a lot about some of the challenges you face in programming with LabVIEW FPGA. And those of you who are FPGA experts are probably going to look at some of my intermediate work saying, ha, 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 ha. And maybe even some of my final work saying, hey, why didn't you consider this? And well, because maybe I didn't know about it at the time. And I do go over a number of things that I learned and how I've managed to create this dynamic time-weighted averaging mechanism that will handle 64 channels with up to 20 samples per channel, while only taking a relatively small portion of FPGA fabric and allowing samples to be at different speeds, because that's what I had in the application. I had some I/O modules that were sampling very fast and some I/O modules sampling very slow. And so since I have been backlogged for 3 years at this point, I am begging, please give me more votes next time.
Cool. Right.
And if anyone is looking for a new puppy, I do have several that are 9 weeks old tomorrow here in Austin that are available for adoption.
What kind?
Labrador mixes.
Well, thank you so much, everyone, here and back at home. And I guess this is the last meeting of the year. I will be posting the semester what we did, so ours and I guess we post there, and then you guys can vote for the next one. Carly said that we will have the dates for next year defined. Yes, December. Yes, so December I will be putting next. Right.
And we'll have an announcement.